here, you'd read stories about quantum computing in the newspaper. And I don't know about y'all, but when I read those stories and the claims that were made, I'm like, I have no idea what they're talking about. Right? It made no sense to me at all. And a large part of that is because they weren't making sense. Right? There's basically something about quantum mechanics that people just don't understand, and it's hard for people to get their heads wrapped around. And so I dug in deep. Right? I went in, and I'm like, it took me a matter of months. And we're talking a lot of watching videos, a lot of attending virtual courses from MIT and from Stanford. And it took a lot of that for me to get to a spot where I'm like, I think I understand this well enough, and I understand how this can work, and I can give a presentation on it. But what's interesting, it wasn't that I wanted to present on what I learned about quantum computing. The quantum information, the quantum nature itself, completely blew my mind to a point that I was like, why isn't everybody talking about this all the time? Right? Because ultimately this is the best that we can understand about the nature of the world around us. And what's even more shocking was we don't understand it. Right? And I'll get to that in a minute. So that's where this talk came from. And then this is like the first half, where I take the first half to describe everything you need to know to understand quantum mechanics. Now, as I said, it blew my mind that when I realized nobody actually understood what's going on here. You may have actually experienced this if you dive into quantum mechanics at all. You quickly get to a spot to where you're like, I have no idea what is being talked about here, because they've taken me to a place that doesn't make sense with everything else that I know, and they haven't led me completely to that place, right? So I don't know what's going on. And most of the time, I don't know about y'all, whenever I'm learning something new, and that's my experience, where somebody's talking about something I don't understand, I think, oh, there's something wrong with me, right? I don't understand this, and I don't even know which question to ask, so I'm just going to be quiet and sit in the classroom and have a question mark appear over my head. Maybe the teacher would see that, but we'll see. But then you start to realize when it comes to quantum mechanics, everybody has this question mark over their head, right? It's like, what's going on? And when I mean everyone, I even mean the dude at the front of the class who's talking about quantum mechanics. That includes me right here talking to you about it. So when I say that I'm going to have you learn everything you need to know to understand quantum mechanics, I'm not talking about everything there is to know to learning quantum mechanics. I'm talking about what you need to know to get past this. Because, again, to illustrate this point, this is Niels Bohr. He's considered the father of quantum mechanics, right? He's the one who, Einstein would be the godfather, grandfather, and we'll go over that in a minute. Bohr was the father of quantum mechanics. And here's what he had to say about this science that he birthed and progressed and actually took over the whole science world for a while, away from Einstein relativity physics to quantum mechanics. He says that if quantum mechanics hasn't profoundly shocked you, then you haven't understood it yet. Here's another famous physicist, Richard Feynman. He's well known for being able to explain physics to people. He also is a Nobel Prize winning quantum physicist. And here's what he has to say about quantum mechanics. Safely say nobody understands quantum mechanics, right? Even the Nobel Prize winning quantum physicist. And this is a professor out of Stanford who did a course that I took on quantum mechanics. And here's what he had to say in the introductory material of his class. He said that you need to have a good mental fight with propositions in quantum mechanics, and that it's psychologically necessary for you to be able to get on top of the subject. So all of this just basically illustrates that this is a subject that you need to actually get to a spot where you don't understand what's going on, and to be okay with that. So that you can then understand, well, what do we know about this, right? And so that is what this presentation is supposed to do. It's supposed to introduce you to the strange weirdness that we don't understand, and to then be comfortable and to sit with that. But then you could then start to ask questions, well, what do we know and what do we understand? So this journey all starts with this question. What is light? Right? We know that fundamentally, when you look around the world around you, things, like if we say that what is fundamentally making up the world around us, it usually breaks down into one of two paths. One is it's either wave, like think about sound. As I'm talking to you now, think about what sound is, right? Sound is traveling, it's energy, a wave of energy traveling through a medium, which is air, that then when it hits your ears, it vibrates your ears. And there are properties to sound, right? Based on the frequency, based on the wavelength, based on the frequency, the amplitude, right? Based on all those things, that will change the nature of the sound that's in your ear. It'll either be louder or it'll be lower, right? It'll be erratic, right? And so all those, we know that there's some things that are fundamentally, the properties are sound. There are other things, though, that are particle, right? And so I think that's initially where we start out from. We're like, if we break this down to smaller and smaller things, and eventually we get down to atoms. At the time that this was coming up, there was still a big question as to whether or not atoms were a thing, right? Well, parts of it. We'll get to that if we need to. But so fundamentally, things are either particles, like you see on the right-hand side, or they're waves. And the question is, well, what is light? Is it a particle or is it a wave? Around 1678, this is a guy, his name is Christian Huygens. Huygens was a physicist, as they were back then. I think pretty much all scientists back then were multidisciplinary, right? But they didn't really have focus, but he did focus on light. And he came to the conclusion that light was a wave. And he had many different reasons for concluding that light was a wave back in 1678, but I'm going to share with you one of them. This is a property of a wave called diffraction. And that is, if a wave hits a hole in a barrier, then the wave will spread out, right? Or thinking about it, there's those terms, but it's basically a wave spreads out. The wave starts from a spot and then spreads out, and that's called diffraction. They're spreading out to different areas. And like you see this wave going through the water here, you can see it spread out and it creates this sort of wave pattern. You can even see the ripples right in there, in that spreading out, that this is the energy of the water being spread out. And Huygens said, when I see a dark room and a hole in the wall, and I see the pattern that the light makes behind it, it makes me think of a wave, much like the previous picture, right? You can see that this light spreads out in that way. It looks like it's diffracting, and so therefore, light is a wave. Pretty solid evidence, looking at that. It looks a little different than the wave. It didn't spread out as much, and you don't see the ripples here, but whatever, it's a good point, strong. Unfortunately, or fortunately, Huygens had a contemporary by the name of Isaac Newton, who quite literally wrote the book on light, called Optics, right? He studied, of course, Newton was a luminary in his day. He's a luminary today, right? What he did and what he exposed to the world was completely different and amazing, probably the most impactful scientist in the history of the world, Isaac Newton. We can argue otherwise, but I'll make that statement. He fits in that category of people. And he literally wrote the book on light, and he said light is a particle. And he had many different reasons for believing that. I'm going to share with you one of them. This is an example of something called refraction, right? And his point here, so you can see the refraction part is, you see how the straw, it almost looks like there's two straws here. One that goes to the surface of the water from inside the water, and then one that continues from the top of the water, because it is refracting, the light is refracting our vision, or how it actually hits our eye. And so what we're seeing here is actually the same straw, just the water is refracting the light. And he said this is sort of like, that's where it's happening. He said this is sort of like, it seems like it behaves as if light, the light that we use to see, is being deflected off of surfaces the way a bullet would. Like it has a specific trajectory, and then when it hits something or causes something to change its trajectory, then we visualize that differently. Right? It would be the same thing as if you're sitting in a mirror and somebody's standing over here. That person can look in that mirror and see you in a reflected way that way. And he says because the mirror is bouncing that particle of light off the mirror to that person's eye to be able to see what is happening there. And so he had other arguments for it as well, but he said light is a particle. And largely because of who he was, he's Isaac Newton. If Isaac Newton tells you something about the fundamental nature of the world, you're probably going to listen to him, right? And so he won the argument, largely because of who he was, not because of the merits of his arguments, although they had merit as well. And so for 100 years, people said, oh yeah, Newton said light is a particle, and so therefore light's a particle. Until this guy comes along. His name is Thomas Young. Young understood the arguments that Newton was making. He also understood the arguments that Huygens was making. And in his mind, he's like, Newton didn't really answer all the points that Huygens, I think is how you say it, didn't really answer all the points that Huygens is making. And since it wasn't answered, and we actually know enough about the properties of waves and the properties of particles, I don't think this situation has been answered. I think since waves behave differently and there are different properties of waves, and particles behave differently and there are different properties of particles, we should be able to come up with an experiment to definitively decide is it wave or particle, not just based on these heuristic examples, but based on just experiment that shows once and for all, right? It's
particle makes sense. A wave, when you're talking about sound waves, a wave is like the way particles move. The medium is moving.
Yeah.
But with light, there's no medium. So how would you describe a light wave?
It's a really great question. In the time that they came up with this, they would say it's traveling in the ether.
In the ether, they would. Okay.
Yeah, they would have said it at the time, right?
Gotcha.
Now, I mean, we would still, you could still argue if you wanted to make this argument. You could still argue. So my sound is happening through the air, right? It's energy traveling through the medium. I don't know what the medium of light would be now. I was going to say you could say air as well, but it happens in space as well, right? And there isn't.
But you said the energy, so it could be a transfer of energy across a distance, I guess.
Yeah, but it's not traveling through necessarily a medium.
Right.
Although apparently space isn't empty, the way that empty space isn't empty. But yeah, that's a great question. I don't know how I would describe it now. That could be one of the reasons why people, well, they would have said the ether back then, right?
Okay.
So that's what they would have said back then. They would have said it's happening through the ether. Obviously, Einstein came along and changed a lot of that thinking. But this is before Einstein. We'll get to Einstein in a minute. Young said, let's come up with an experiment. And here was his idea. And in particular, he was talking about the property of waves and how waves interfere with each other. You think about particles. Particles, when they hit each other, they bounce off at whatever trajectory and they remain particles just with different velocity, right? And momentum. So that's how particles interact. But how waves interact is they kind of blend in, right? And so he's saying that facet of the way waves work and the way particles work, we should come up with an experiment to show. And in particular, you don't see this, but on the other side of that guy's head, there's another ball there. And he's making waves, two different waves at the same time on the water. And you can see that as the waves blend in, there are some places where the waves, the peak of one wave matches the peak of another wave, and it amplifies that wave. There are other places where the peak and the troughs meet each other, and they cancel each other out. And in particular, that cancellation of peak and trough, you can see happening right here. Right? Those smooth spots in the water are where the peak of one of those waves is matching up with the trough of another, and basically cancels out the wave effect, and so it just remains this smooth surface, right? And so Young actually wrote, this is the diagram he wrote, and he said if we had something that had two light sources at both A and B, and it was a wave, then those waves should interfere with each other, and you should be able to see in places like this, where the peak of one and the trough of the other met each other, that it would cancel each other out. So when that light resolved on the wall, you would see bands of light interspersed with bands of dark. Right? And the dark spots would be wave and trough, and the bands of light would be, peak and peak, right? Peak and peak. And so he said you would see those dark spots at C, D, E, and F. He didn't do the green lines, I did that, but this was actually his drawing.
Neon green.
Yeah. And so this is not his drawing, but I wanted it to be simple, right? He came up with this experiment. Rather than using two light sources, you use one light source, and you shine it at a box that has two slits. And this is, you probably heard this described, it's Young's double slit experiment. It is like probably one of the most famous experiments in physics, right? Aside from Newton being hit in the head with an apple, right? This is probably the most famous experiment, Young's double slit experiment. And so the idea is you have those two slits. When the light hits both those slits, it will create two separate sources of light. And if they're waves, then they will interfere with each other through the box. And then when you see the pattern at the end of the box, it will either be two light spots, if it's particle, or if it's interference, and you would see bands of light and dark interspersed. And so he built the box, turned the light on, and that's what he saw. This is called interference. This is waves interfering with each other. So he proved with this experiment, once and for all, absolutely, light is a wave. Okay? And there were other experiments as well that were even more solid that came later, but this is the one that everybody talks about. Right? So light is absolutely 100%, we know light, with certainty, we know that light is a wave. Right? But then 100 years later, this guy comes along. Einstein. I told you we talk about Einstein. Einstein came up and said, no, light's a particle. He knew about Young's double slit experiment. He knew that light was proven to be a wave. But Einstein is not the type of guy, well, let's put it to you this way. He's not the type of guy to say something was proven, it can't be disproven. But even better, this is a better facet of Einstein. It's not like he was trying to disprove the wave theory. He was the type of guy that could say, oh, why not both? Right? And to really expand our understanding, right? That's a feature where you can hold two ideas that you think are contradictory. That'll either make you crazy or make you wise, right? One of those two, right? And so he looked at this and said, all right, light's a particle. And the way he came up with this was back, by the way, this was 1905. This was his miracle year, right? This was the year that he wrote the paper on relativity. He was a patent clerk, right? And so not even working in science necessarily, he's a patent clerk. He wrote the paper on relativity. He wrote a paper on atoms to actually show that atoms exist. From that, he was evolved E equals mc squared on the relativity paper. So the most famous equation in science, he came up with that, 1905, and then he wrote this paper, which is about the photoelectric effect, and I'll describe that in a minute. But this is the paper he won his Nobel Prize on. It wasn't relativity, it was the photoelectric effect and quantized energy. Okay, that's the quantum, it's quantized light energy. And the photoelectric effect, let me see if I have, nope. I had different versions of this, I had different slides here as well. Because I need to explain this to you, and this is not easy to understand. Basically, at the bottom there, that rectangle is a metal, and it has electrons in it. That's what those negative circles are, right? And what they found, when light was a wave, there was a phenomenon that happened to metals when you shone light on it that made no sense if light is a wave. And that phenomenon was photoelectric effect, that if you take a piece of metal and you bombard it with light, it will release electrons from that metal, right? Now what's surprising is it doesn't matter how much light. The intensity of the light doesn't matter, right? It is only the frequency of the light that matters. So if you bombard it with red light, then electrons would never be released. If you bombard it with violet light, then electrons would be released. And you could do it with a small intensity of violet light, it would still release the electrons. And the reason that's surprising is if light is a wave, and it's wave energy that's going into the metal, it's absorbing that wave energy, that electron release should happen after X amount of energy is absorbed. But the point is, you could flood it with as much red light as you possibly could, and it would still never release an electron. And so Einstein's paper said, it's as if what's happening with this light is being delivered in quantized packets of energy, or photons, and they act like particles. It was like the red lights would be like you trying to move a bowling ball, or you trying to move billiards with a feather, right? It's not enough energy in that quantized packet. But if you do it with violet light, then it's like you throwing another, marble at it or whatever, and cause it to move, or another bowling ball, or another ball of some type that you actually cause it to move. That's quantized packets of energy. And that's, the term quantum actually, interestingly enough, I didn't put this up here, but you guys would appreciate this. Planck actually came up with the math to show that there was quantized packets of energy, and just thought that there was something funny in the math, that it didn't really work out in the real world this way, right? That it worked out in the math, but it doesn't really describe reality. It turns out it described reality. So he's the one that came up with quantum in this formula as an abstract mathematical concept. Einstein applied it to the real world, to the real physical world in this way, and said, this is an example of Planck's quantum operating, and so light is now a particle. And as I said, Einstein had no problem saying, yeah, it's a particle. But Young proved it's a wave. Yeah, I know that. Right? And so light is both wave and particle. In some circumstances it behaves like wave, in other circumstances it behaves like particle. I don't know why. I always expect there to be an applause at this point. But doesn't count. I had to ask for it, right? Besides, it wasn't me that figured it out. It was Einstein. You're applauding Einstein. So then what does that mean, right? Now we have light as being both wave and particle. We don't know what that means. Nothing is both wave and particle. We had no experience of that. So what does that mean? And so in this case, what they thought is, what if we, as part of Young's double slit experiment, if it is a particle, so if the photons, so this is an example of the double slit experiment where each of these individual dots are individual photons. And of course, if it's a particle, then those photons would have to go through one of those two slits in order to resolve on the back wall, right? And so they said, but it looks like it's a wave. It does a wave pattern. Maybe we can learn something if we could observe which of the slits that photon goes through. And we can actually identify, all the photons that went through the right slit resolved this way in the pattern, and all the ones that went through the left slit resolved this way. Maybe that would give us some better things to look at and some different things to look at and give us some more knowledge here. And so they said, well, let's do that. Let's observe which of the slits that the particle goes through. And so they did that. It's my little eyeballs observing which of these slits does it go through. But then once they did that, once they started observing which of the slits they went through, the pattern on the back wall changed.
What does it mean, observe? What did they do to observe?
It's a great question. Let's handle that after the fact, right? That is a great question, because that leads to how observation requires interference, right? Because we're talking about things that are so small that you think about a photon, in order for you to observe something with your eyeball, a photon needs to hit your eyeball. But now we're talking about we need a photon to bounce off of that photon to be able to see it, right? That would actually clearly be the observer. In order to be able to observe, it would actually affect the outcome of the experiment, right?
You showed us those bands. Was that a photograph? Because wasn't that an observation?
Yeah. We'll get to that in a minute. We'll get to that in a minute. It is an observation. It is.
We're all confused here.
I would look at it this way. I would look at it this way. I say I do look at it this way, and any real physicist would really cringe at what I'm about to say, so take it with whatever amount of salt you need to take it with. But I would say that, actually, let me show this first and then I'll say this, right? I'll say that light behaves like, I'll talk about the quantum realm. The reason I want to roll my eyes at that, because we have things like Ant-Man that I roll my eyes at all the time, right? And they talk about the quantum realm and all that. I still view it that way for understanding reasons, right? And I'll explain to that in a minute. So once we observed, once we could detect which of those slits it went through, then the resolution on the back wall became particle. It was as if it was a wave, and then it resolved to a particle. Okay. Once you take the observation away, it resolves on the back wall. In this experiment, if you think about it as a wave, so to answer your one question is, isn't this an observation? Yes, it is an observation, but on the photon on the back wall, not an observation at this point, right? And so any of these photons on the back wall, you cannot tell which of the slits those photons went through. It's possible that a photon that went through that slit, based on the wave nature, because if we talk about a wave, that photon could show up anywhere in that wave, even way here on the right, interfere with the other wave, and end up way over here. A photon going through here could end up way over here, right? And so, while this is an observation of that photon at this point in time and space, but you don't know about it at this point in time and space. Okay? Does that explain that question?
Yeah.
Okay.
Explain the difference between the observations.
If you're
Yeah,
curious,
it gets a lot stranger than that, and we'll go over delayed observation here in a minute. Right?
Just stick a cat in a box. That'll help.
We'll talk about that in a minute. We'll talk about that in a minute. And so the problem is, what we're saying here, and this is what has become known as the Copenhagen interpretation. The Copenhagen interpretation says that light begins as a particle, a photon. It travels as a wave until it is observed, which that wave, so when it travels as a wave, it could be anywhere on that wave. But then once you observe where it is, it collapses to that particle of certainty once observed, right? So it's still traveling as a wave as it goes through those if it's not observed. But then what you see on the back wall, the fact that you actually even see a photon means it's collapsed, right? That's the interpretation, the Copenhagen interpretation. There are other interpretations, some of them gaining more ground now. But this is where it gets to be very confusing, right? And this is why earlier at lunch I was saying to people that this may be something that we never be able to understand. And this is why. Because what is required for science? Right? One of the fundamental things that science needs to be able to do is to observe phenomena, right? And yet what we're saying is observation has an effect on the outcome of this experiment. That observation changes the nature of reality, right? And so how are we, in order to do this experiment properly, to see if observation has an impact, we'd have to come up with an experiment that we couldn't observe the results. How do you do that? Impossible. You can't do that, right? They tried it. In 2000, I'll tell you about the delayed choice quantum eraser double slit experiment here in a minute, because I don't have the slides for that. It's not part of this presentation, but it is completely mind-blowing, right? But in this point, Max Planck, who was the one who actually did the mathematical formulations to find the quantum and came up with the name quantum. Max Planck, when he came to the realization what's happening here, this is what he has to say about science's ability to solve this, to understand this fundamental nature. It's because we're a part of this whole natural phenomenon. We will never be able to really truly understand it. Right? That's what he had to say. Now, I'm going to blow your mind a little bit further. This is a picture of a laser, a green laser, doing the double slit experiment. I've done this presentation before, and I didn't do it this time, where I'm using a laser pen, and I'm pointing at things. And I actually have a very small, on the very end of the pen, I have a very small double slit box on it. And so, but when I'm pointing it away, I can point it up at something, and they're like, okay, great. But then I have to turn all the lights out, and I shine it far enough away on the wall, you can see it. And the whole illustration point is, this is the quantum realm. Like, we live in this world, right? That quantum is happening all around us, and we don't even know it or realize it. That this light is traveling as a wave, only to resolve as a particle, if you believe the Copenhagen interpretation, upon observation, right? That's when it resolves, and that's happening all around us. But I also, at this point, I thought, Einstein kind of stretched a little bit here. Maybe some of y'all thought about this as well. I said, I think Einstein's stretching a little bit because, okay, fine. Light as a photon behaves like a particle in that it doesn't spread out as much, right? And, when it gets observed at the slits, it ends up with a blotch on the back wall. That's kind of like a particle. So it behaves like a particle in that way. And you can actually even count the amount of energy in this quantized packets. So there's all of that. But if you ask me, like, the one base fundamental thing that a particle needs is it needs mass for me to call it a particle, right? And light does not have mass, right? And so I'm like, Einstein is kind of mixing apples and crab apples or whatever, right? And so I'm like, yeah, that's neat, but there's something fundamentally different about light. That's the thought that I had. And then I came across this. This is an experiment done with electrons, a double slit experiment. You can see an interference pattern there. Electrons have mass, right? They've done the double slit experiment with increasingly larger and larger complex molecules. This is a carbon molecule. I think they call it a buckywell. I think it's after Buckminster Fuller. But it's a carbon molecule. I think it's 64 different atoms, carbon atoms, put together in a way like this. They've done the double slit experiment with buckyballs and seen interference. So we're talking bigger and bigger things, even to the point of Schrodinger's cat, right? So the idea is everything exists as a wave of probability until observed. Everything. Now this is where it gets to be really troubling, especially to physicists. Well, first let me say this and I'll talk about Schrodinger's cat. Physicists, the most common response to physicists when you ask them, what is the interpretation here? Is it really observer-dependent reality? Einstein was never comfortable with that. Einstein never liked observer-dependent reality. His phrase was, I like to think that the moon is there whether I'm looking at it or not, right? So he's never comfortable with that. A lot of people like to say that he was uncomfortable with the probability of reality. He was at first. We said, I like to think God does not play dice with the universe. That was his statement. He actually came to terms with that. He was okay with us living in a probabilistic universe, not as deterministic as maybe we thought it was. But when it came to observer-dependent reality, he didn't like that idea at all and never solidified on it. He tried to actually resolve that. And he'd get into some really epic debates with he and Niels Bohr. And Niels Bohr won out on all those debates. Right. So there's a book I could recommend that is kind of mind-blowing when you go through the thought experiments that they would have. But buckyballs and Schrodinger's cat. Now here's an interesting thing. Einstein did not like observer-dependent reality. Erwin Schrodinger also did not like observer-dependent reality. He thought it was ridiculous. He thought it was the most ridiculous thing he'd ever heard. Like, what are you talking about? Obviously, reality isn't dependent on whether or not we're observing it. Trees make sounds in the forest when they fall, blah, 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 right? Schrodinger came up with Schrodinger's cat experiment, which, just to make it, I'm sure all of you have probably heard of it, but just to let you know, the whole idea is that the reason Bohr got involved in all of this is Bohr created a model of the atom with its electrons and orbiting, was it protons? Orbiting electrons? Anyway, with orbiting electrons. He came up with the idea, because back then it was like people thought that the orbitals were like moons or satellites to a planet, and they were just orbiting. What they found out was they don't travel, and actually they don't even orbit, because there was an understanding that the orbital rotation in an atom would lose energy and would then cause the electrons to crash into the nucleus. And so therefore, you shouldn't be able to have atoms with that understanding. Now with the quantum understanding, these orbitals are things that hold the atoms or hold the electrons, and the electrons can then just transport orbitals. They don't travel, they move from one to another once observed, right? Now this, obviously, we're using a much expanded concept of observation. I put the eyes up there just to illustrate a point. But I would say, this is where I get into the quantum realm. I would say that in the quantum realm, or quantum reality, things exist as a wave of probability. And when that when that wave of probability interacts with our classical world, our classical universe, then that's when it resolves. Because if it interacts in our classical reality, somebody may not be observing it at that point, but could observe it, right? You could actually, whatever physically happens in the world, engineering-wise, you may not be able to, but physical-wise, you would be able to see what happens anywhere else in the world and be able to recreate that particle hitting that spot, right? Or being in that place. And so when it reacts, hitting the wall is a reaction to the classical or physical space.
So just asking about that, have they, I'm sure they have, right, had two independent observers, and do they find that it's deterministic, the end state of whatever they're observing? Or does it depend on the observer what the actual end state is?
No, it depends. Your observation of it resolves that particle, that wave, for our entire classical universe.
For everyone, okay.
For everyone.
So if I look at something and someone else independently observes as well, they'll see the same thing that I see.
Well, then you get into relativity of time, right? Because one of you are going to be observing it before the other.
Right.
And so, yeah, they will see the same thing, but whoever observed it first is what caused the wave collapse into a particle, right? And but then again, what you saw in the double slit experiment, after it traveled, once we observe it at the slit, it actually goes from that spot on as a new source of a wave. It travels out as a wave. You see a blotch because it just so happens it's small enough, right? It wouldn't be way over here. If you actually push that wall out further, you would see the blotch be really bright in the middle, but then get dimmer and dimmer and dimmer and dimmer all the way out to the edges at any place that wave could resolve on that back wall. Right? And so it's a particle here, but then as it's traveling, it transports back into a wave of probability anywhere on that thing it'll be. Most of them, the probability is mostly to be in the middle, but less probable to be out on the edges. Right? Does that answer?
Yeah, I was just curious.
Because we'll get into delayed choice double slit experiment as well.
Okay.
But Schrodinger came up with Schrodinger's cat because he's like the idea of quantum electrons around a nucleus of an atom, and how it's actually a nucleus cloud, right, rather than an orbital. And the idea is when you have a radioactive device is a device or a substance. The substance will lose electrons, which means those electrons need to be resolved from a cloud of probability to a particle of certainty. And if you're not observing it, then they can't be resolved. And so we're saying that there is no radiation happening on a substance that's radioactive if there's nothing there to observe it. And so in his mindset was, let's place the radioactive substance in a box, let's place a cat in the box, and then let's make it so that there's a detector that if it detects a radioactive particle released from the substance, then it will break a hammer, it will use a hammer to break a vial of poison, and that poison will then kill the cat. But what we're saying, because we haven't resolved the status of that particle, that there are two realities right now in the future, that cat is both alive and dead, because we had to create those two probabilities based on the resolution of that particle or not. And so that's why he said the cat is both alive and dead. That's where it becomes absurd. This part I can kind of understand. The part where it's actually radioactive decay, and maybe it's not decaying if you're not looking at it, but that then posits all these other things that could happen later, including the cat being both alive and dead, and that's obviously absurd, right? And so therefore, and yet now people talk about it as if it was, some proof or example. And the truth is, this is something you're never going to be able to resolve, right? Because once you open up the box, it all collapses into one of those states. And so you don't see both of those states at the same time, right? It collapses to one of those. Okay, I held off on some of your questions. Did I answer, was there?
I think you did. I imagine the observation is any form of detection, right? So like, for example, if you shown the light that slits, didn't look at it, then turn off the light, and then you felt against the wall to feel where there was heat, that's a way of observation.
Yeah, that's an observation. Yeah, and I'll go, so we'll get into the delayed choice quantum eraser. So at first, and there were people who were steeped into this, and people still today, it's a fringe idea, but there are people who think it's relies on a conscious observation. Like it requires a conscious observer. A lot of physicists get really mad when you say that, right? They don't want to believe that.
I wasn't warm until I thought I was warm.
Maybe we can't understand it because objective truth is a wave of particles, and none of us can look at it, and it won't resolve until we look at it.
Yeah. This quickly gets into the realm of philosophy, because what do you mean by observation? Does it need to be a conscious observer? Right? This is why most physicists will, because there's other interpretations, like the many worlds interpretation, which means every place a particle could be, it actually is. It just spins off another universe for that particle to be there. Right? That's the many worlds interpretation. That's the one that's gaining ground, by the way. That's the thing that's kind of amazing to me. But the main point is most physicists, there's a physicist by the name of David Merman, who basically said, here's the proper interpretation of what's happening in quantum mechanics. Shut up and calculate. That was his response. It's like the calculations produce results and let us do amazing things in our world. That's what we need to do. Don't worry about what actually is really happening there. Leave that to the philosophers. So most physicists don't even try to wrestle with the question, right? That's why it gets into the realm of philosophy. So when they started talking about conscious observer, one of the first things they did for the double slit experiment was they then just took a camera and recorded the observation of which slit it went through in the camera, and then later observed what was on the camera and saw, oh yeah, it resolved. Right, that non-conscious observer of the camera actually resolved the particle on the back wall. Right? So it doesn't require a conscious observer. But then the delayed choice quantum eraser double slit experiment came in 2000. It was first done, I think, University of Texas. No, Texas A&M. And it's a fairly complex setup, but just basically understand that in the double slit experiment that they created here, they made it so that you could, after the particle resolves on the wall, right? So you have the double slits. You then pass information about those double slits, about which slit a particle went through. So you have a particle that goes through a slit. You send that information into a device. And that device holds on to that information as to as to the fact that it went through this slit. You hold it into that device, and then after the particle has been resolved on the back wall, at that point, you then make a choice to decide whether to destroy that information or to observe it. Okay? Thinking, we got it now, because that particle's been resolved. Right? The information that it went through this hole has been resolved on the back wall as a particle, right? But later on, we're going to destroy that information, right? And we're going to see where did it resolve on the back wall. What they found out was after the time that that particle resolves on the back wall, the particles that they later on destroy the information about which slit it went to resolve as a wave pattern, as if it had never been observed.
Wait, so they like observed it, but then so like it was observed kind of not through them, and then they didn't look at it, they got rid of it, and the particle kind of knew?
Yeah. Yeah. It is an example of retrocausality, possibly. Maybe not. But the idea being that something that happened later affected something that happened prior. Right? That's the thing. And that also, in my mind, it puts the idea of a conscious observer back on the table. Because again, what are we doing at the end? We have to observe it or not. And if we don't observe it, it's going back in time and resolving it on that wall as a wave. Yeah. So the reality is, again, it just kind of solidifies that as long as we keep trying to observe this, we're never going to know what happens. And so what do you do with that? We need a completely different science. Like somebody needs to come up with a completely different science that has a completely different paradigm. I don't know what that is. I don't know if that's possible. Well, unless you want to get into philosophy and we can talk about religion and all that kind of stuff. Anyway, that's all I got.